we're gonna start where we left yesterday, which was, I mean, I threw the pages, but basically we were stuck in computing integral of x squared e to the x dx. Okay, this is what we were stuck with, and now this by parts thing can be applied to the definite integral result. Just take like a stupid example from 0 to 1. Okay, nothing changes. The only thing that's gonna happen is we're gonna carry this 0, 1 across all the integrals that we're gonna do. So nothing special. Okay, this form, and I'm gonna say it again, this form, or any form of the type xn e to some ax, something like that, is by parts. This is solvable 100% by parts. The way you do it is if we write our theorem again, which I hope I remember. Yeah, I should. Okay, integral of u prime v dx plus integral of v prime u. Let's actually keep the order. U v prime dx. Okay. Remember, the challenge I said with the by parts is not remembering the theorem or the calculation. It's just choosing which one is u and which one is v. Remember I said that? I think I mentioned like 20 times. So I'm going to tell you, whenever you have this thing to solve it, you need to take x to the n as the no derivative part. So no derivative, and e to the ax as being v prime derivative. Okay. This is how we solve this type of problem always. Okay. Now, why is it? Am I just creating this out of magic? No. The idea is that if you take e to the ax as the derivative, then when you write your formula, you're going to have to take a derivative of xn. Okay. What happens to power functions when you take a derivative? The coefficient just goes down. Okay. So the idea is that if I do this enough times, that coefficient is just going to disappear. And I'm going to be stuck with integral of exponential, which is easy to integrate. Okay. Let me show you what I mean. So let's solve this x squared. You're going to see that x to the third or xn or whatever you want to call it is going to be the exact same. So let's solve this one. So again, reiterating my problem, this is what I need to solve. Let's just keep it 0, 1 because we haven't done any definite integrals. Okay, and I said I'm going to take x squared as being u, and I'm going to take e to the x as being v prime. Okay, of x of x. Now, u prime of x, 2x. V of x, exponential is nice, never changes. So e to the x. Does that, okay, just so you don't call me on I'm simplifying the problem or whatever. I hope everyone agrees that I could just put like an e to the ax here and it's not going to change the whole solving of the problem. I'll just have like an e to the x a here or something like that. It wouldn't matter. So I just think it might be distracting for some of you to just focus on the integral, on the derivation rather than the process. So that's why I'm thinking the simplest I can find. Okay, now I have all my elements, all 4 of them. So I can just replace. So I have u and v. So I have ux squared v e to the x. And now in the definite, since I want to have the definites from 0 to 1, I'm just going to say evaluate this between 0 and 1. Now write the integrals. X prime, u prime, I mean, is 2x. V is just e to the x dx plus integral again. Don't forget the 0, 1, like I did. U is x squared, v prime is e to the x dx. So again, isolate what we know. This is what I have. So this is what I want to compute. 0, 1, x squared e to the x dx is equal to x squared e to the x 1, 0. minus this integral, which I can write as 2, 0, 1 x e to the x dx. Everyone follow on that? I just move this thing on the other side. Okay, now this thing here, if I value it, it's going to give me a number. It's going to give me 1, I think, or e, I don't know what, something like that. This is going to give me a number. This, on the other hand, I don't know. I need to compute this one. Okay, and look at this. I have the same integral as before. You know, let's put it here. And you can zoom. Yeah. So I have the same integral as before. The only change is that x is at a lower power. And that is the key of solving this type of problem, general case. The key is that when I apply by parts this way, the power of x goes reduces by 1. So now you can guess, if I apply by parts to this thing again, the power of x will decrease again. So it's basically going to disappear, and I'm going to be stuck with an integral of e to the x. So let me show you again. We're going to do it again. We have to compute this. This is again the by parts. You can use it. You can use by parts just like you can use L'Hopital any number of times you find it necessary. Okay. Okay. So now we were aiming to compute this x e to the x dx from 0 to 1. And we stick to the same recipe. We take x as being no derivative. We take e to the x as being derivative, the derivative. So then u prime of x just is 1. And then v prime, just v of x is equal to e to the x. So now that you look through your notes or whatever, does everyone understand the process that I'm doing here every time with the by parts? It's like the same every time. It just, once you have the choice, you just plug it in. The key part is this choice of u prime and everything. Does everyone get what I'm doing here? Okay. Just ask it now, because it's, yeah, if you don't get this, it's not going to get better. Okay. Now, I just applied the formula. I'm going to write the formula again. U times v integral u prime v dx plus integral u v prime dx. So I can just replace, and I get uv, so x e to the x from 0 to 1 is equal to integral from 0 to 1 u prime, which is 1 times e to the x dx plus integral u, so that's x, times v prime, that's e to the x. Oh yeah, sorry about that. Apologies. Okay, again, 0 to 1. If you have a definite integral, if you need to compute a definite integral, just put it 0 to 1. Keep the margins on each of the integral, and integrate the left hand side. Now, what do I see? I see that this is what I wanted to get. So I'm going to have integral x e to the x dx 0 to 1 is equal to x e to the x from 1 to 0 minus integral 0, 1. And I'm going to write it like this still, just because I think it looks nice. Okay. So I applied the by parts again. Okay. And now I only have integral from the exponential, which is really, really nice. That was my whole plan. When you see this type of xn to the ex, you just got to know that if you apply by parts to it, the xn will eventually disappear, and you're just going to be stuck with the exponential, which you can compute. Okay, I'll write it in a different way afterwards. Let's finish the problem, then I'll write it in a different way. So this is just integral of e to the x. So this is just e to the power of x from 1 to 0. So I can write that 0, 1 x e to the x dx is equal to 1 times e to the power of 1, I get 0 times e to the power of 0, minus parentheses, e to the power of 1 minus e to the power of 8. Okay, this just gives me, does this even give me 0? Oh no. Okay, this just gives me 1. Just do the math. This cancels out, this cancels out, this is 0, and this is minus plus 1. Okay, so this is just ignore that, don't stress it out. So I computed that this thing is equal to 1. And I can take this and plug it in here. Okay. So just plugging it in there, I get recopy my function from the other page. X squared e to the x dx is equal to x squared e to the x 0, 1 minus 2 times this integral that I just computed and I got it 1. Okay, this is 1. So my integral that I was aiming to compute from the start is just equal to 1 times e to the 1 again. 0 times e to the 0 minus 2 times 1. This thing just gives me e minus 2. Okay, and I'll show you that. I'll look that up. So this is, this is 1, and this is okay. Now that we have computed, here's the idea. We started with x squared e to the x. Okay, I applied this by part to it. I ended up needing to compute x e to the x. Okay, I still don't know how, so I don't know what this is. I don't know what the integral of this is. I don't know what the integral of this is either. If I apply again by parts, I'm going to get e to the x, and this I can compute. Okay, so if I can compute this, I can then just go the other way around, compute this, and then compute this. This is our train of thought. We started with this x squared e to the x, and we applied the by parts to it in the way I said you should apply it, and you get to this formula. In this formula, this is known. This is where you started at. So you need to compute this thing. Okay, this thing only has an x here. It's the same thing but has a lower power x. Whenever you have lower powers, it's usually a good sign. It usually means that you can solve it. Okay, if you go negative minus 1 million, that's a bad sign. But if you have like smaller positive powers, it's a good sign that you're getting close to solving it. So this one, I see x e to the x, and I think, hey, I can just apply by parts to it again. So if I just apply my parts to it again, right here, just taking the same notations I used to, I get here. And the difference this time is that this is done, this is computed, this is what I started with, and I can compute this without by parts. It's just an integral of an exponential, okay? So just the exponential. So that's the idea. The problem is if you take the other way, you take the other choice here, you take the problem is, let me write it actually up. The problem is if you take the other way around, which is x is equal to x squared is equal to u prime of x, and then e to the x is equal to v of x. The problem with this is that your powers will grow. Okay, your powers will grow. What do I mean by this? Well, let's take an example and I'll show you. I mean, let's actually solve this one, okay? X squared is equal to u prime of x. So u of x is just integral of x squared dx. So u of x is just x to the third over 3. Then e of x is equal to v of x. So v of x prime is just equal to e to the power of x. Okay, everyone. Okay, with this, we're just doing the outer case. See what happens. Why don't I want to take this one? Write the formula. Okay, now replace, and I get x to the third over 3 from 0 to 1 is equal to integral from 0 to 1. I'll lift it up. So I'm just trying to keep the other one as well. U prime was x squared. V is e dx. So this is my fraction that I need to compute. Plus integral 0 to 1. U is x to the third over 3. And this is e to dx again. Dx. Okay. So let's compare our situation right now. Okay. This is what I got in the bad case. When I did it according to my suggestion, we got this. Got x squared times e to dx. I think I missed an e to dx here. Doesn't matter. 1, 0 is equal to integral of 0, 1 to x e to dx plus integral 0, 1 x squared e to dx dx. Okay? These are the two cases. These are the equations we got in the two cases. This was bad case. This is my case. Now, let's just compare them, okay? See why I'm saying, let's, hopefully understand why I'm saying do not take this bad case because you're never going to finish and you're going to panic. So this is what I want to compute, okay? This is what the problem asked me to do. They're asking me, I should bring more politics, right? This is what I'm supposed to compute. So it's in both of them. That's fine. Left-hand side is fine in both cases. I just replace and I get a number, so I'm good. The question is this easier to compute or is this easier to compute? That is the question. Is, integral of, I'll just write it like this, x 0, 1 e to the x dx easier to compute? Easier than 0, 1 a third x to the third e to the x dx? That is the question. And the answer is yes. The problem is you can't even compute this. You got to apply. There's no way you can compute this. Literally no way. Unless you just do by parts like 4 times, 3 times. Okay? So that's the idea. You see the exponent. Let's put a 1 here. The exponent is smaller in my case. So it means that if I apply by parts to it, again, I can get rid of it. This will just grow. If I apply by parts in this case again, I'll get x to the 4, x to the 5th, x to the 2000. You're never going to finish the problem. Okay? While in our case, if I apply it this way, I'm going to get rid of this x, and I'm going to be stuck with just an integral of e to the x. Integral of e to the x, good, I can compute. Integral of x 2000 times e to the x, bad, I can't compute. Does that make sense? Do you see the difference? Why I'm saying one of them is the bad case, one of them is the good case. One of them gives you higher and higher powers. You'll eventually end up. So I asked you to compute x squared e to the x dx, and I saw last year. Some of them, some results said, "Oh, I can only compute this if you tell me integral of 1 x to the 10th e to the x dx." And I'm like, that's more complicated than the problem we started with. The poor kid just applied by parts 10 times the wrong way. And he got x to the 10. And if I didn't tell him to stop, he would have just went to, I don't know, 2000. He would have still be applying by parts right now. Okay? It's not a joke because realistically, this will happen to some of you, okay? I'm just trying to avoid that because imagine spending this much time in the exam, taking by parts 20 times and not realizing you're in a bad situation. And then after 2 hours, you're like, oh shit, I haven't done anything. So notice when the problem that you have to compute is actually more complicated than the problem you started with. Like this, again, bad. From here, my solution takes us to x e to the x, which has a smaller power. And then if I apply it again, I just get integral of ex dx, which is good. This is easy to compute. If you go this way, you get x 249,000. And I wish you the best of luck. I'm never going to compute that for you. Okay, really, really important. Now, if you have any questions, just let me know. I hope it was clear. And I don't think it's ever enough emphasized because the whole trick with the by parts is just to choose your U and V correctly. As you can see, I'm not doing any complicated math. I'm just choosing the U and V to satisfy my thing. Now, another case where the by parts is a classic application is when you have stuff of the type xn log of x. Okay, now this is slightly different. So again, this is xn ln of x classic by part. We actually did this, I think, yesterday. But maybe I just didn't want to emphasize this. I knew you were going to panic if I went into this all that. So the idea is, what am I going to take as U and V here? And maybe this is more intuitive because you never want to integrate log of x dx. This is not something you want to integrate. Okay. So if you don't want to integrate that, the idea comes, take log of x as being no derivative. And take x to the n being u, okay, derivative. Okay? Because again, the other cases where I take the other case, I'll just write the reasoning. The other case is taking ln of x is equal to v prime, right? That's the other case where I take ln of x as being the derivative. In which case, my v of x is just going to be the integral of log of x dx. And unfortunately, you guys don't even know how to compute that. Okay? And even if you knew, it's still going to be ugly. So I would, before you try to compute integral of log of x as it is, I would be relatively sure that this is like the only way that's gonna work out. Okay, because dealing with that thing is not nice. And it's gonna be a lot of complication. So yeah, this is the whole idea. I can do it. Let's see what, yeah, I didn't even see. Okay. Yeah, we can do it right now. So again, I said from here, take ln of x equals v, means that v prime of x is 1 over x. I mean, yeah, it's just a derivative. And then if xn is equal to u prime, then u of x is equal to integral of xn dx, which is xn plus 1 over n plus 1. Okay. Either apply the formula or just think how I think. It's okay. Cool. Now I know the formula. I'll write it probably like 20 times before we finish this class, so that's fine. Or you're learning it. U, no derivative. on v prime dx. Okay. First question. I don't. The examples I'm giving, I don't know the correct answer. So, and I'm really not a fan of computing, as you probably tell. But does everyone understand that it's the same exact problem if I just put like some definite integrals here? I just got to replace the values in. Is everyone okay with that? Like, if, for example, I just put 1 and 10, all my equations will just have 1 and 10 to them. And I will just replace here from 1 to 10. Does everyone understand that? Okay. Or do you guys want me to carry it across for one more exercise? It's exactly the same. Since I already wrote it, I guess. Okay, now let's just plug in our things. U is xn plus 1, n plus 1 times v, which is log of x from 1 to 10, which is equal to integral from 1 to 10 of u prime xn times v ln of x dx, a little bit too big, plus integral 1 to 10. I have u here, so I need to use this one, xn plus 1 n plus 1 times v prime 1 minus x dx. Okay, just apply the by part. And now hopefully you see why this choice of taking ln of x as the underivative makes everything so much nice. So left-hand side, this is done. There's nothing I need to do here, outside of just plugging the numbers. This is where I started. And this is what I have left. So always when doing my part, it's good to have the clear structure in your head. This is this is done. This is where I started, and this is what I have left to compute in order to get my final result. Okay. So again, my integral that I was asked to compute in the start, this ugly thing, is equal to this thing minus what I have left. So this thing, integral 110 xn plus 1. I'm not going to touch it for now, for a little bit. And why am I saying it's important to have a good structure in your head? Because you can ask yourself, hey, is this thing actually uglier than what I started with? Like it wasn't the case. It would have been if you took a wrong idea. It's good to ask yourself these type of questions. Am I getting better? Am I getting worse? Maybe I should try the other one. Okay, this is the time, because if you just avoid it for too long, you might spend another 15 minutes computing this, another 15 minutes panicking, and then half an hour is gone, an hour is gone, you haven't written anything down. You're panicked. And at that point, the exam is 10 times harder than it should have been. Okay, now, why did I use this writing? Because x goes away with x here, so what I have left is just the integral. What I have left is integral. Sorry for that. What I have left is this thing, which again is just plugging in numbers, so this is not bothering me. Minus, what is this? Integral from 1 to 10. Oh, again, I can take the n plus 1 out because it's a constant. Xn dx. And this is really nice to compute. So at this point, I'm like, yeah, I'm definitely on the right track. I did something right because now I can compute everything. So I'll just write I can just write the answer. Integral from 1 to 10 xn x dx is equal to this thing. So just 10 to the n plus 1 over n plus 1 log of 10 minus 1, it's the n plus 1, log of 1. So this was the first integral, something like this. And then I'll have minus the second integral, which is n plus 1, which is right here. That is, this integral we already computed is just, this is just xn plus 1 over n plus 1. So it's just 10 to the n plus 1, n plus 1 minus 1, n plus 1, n plus 1. And yeah, I'm not interested in computing this. Something. Okay. If they wanted me to compute, they would have given me a power for n. So I don't need to stress about it. Obviously, I can make some simplifications, but we don't care about them now. So any questions about this? How we did it? Again, the choice made it all. And now, I don't know where else you could use by parts. The applications are limitless. Like obviously, you can create problems that can be solved with the by parts. But these two examples are like this one, xn e to some ax or something, and then what was the other one? Xn log of, I don't know, ax or something like that. Anything of that sort. These are textbook examples of the by part. Okay. These are like way older than I am. So when you see this, you should think of applying by part and be careful to apply it correctly because there's a risk of never finishing the problem you start if you do it the wrong way. Okay, now let me see. We have an interesting example. I was thinking of doing some like exam problems actually for this, but unfortunately, we're kind of pressed by time. I said in the schedule that I gave yesterday that we're going to do substitution Monday. Well, I'm going to give you substitution today if there are no questions here, and then we're going to do more exercises on Monday. Before that, how do we define? Because maybe you're going to see, maybe you're not going to see. I actually don't remember. If you have something like integral from 0 to infinity of some f of x dx. How do you compute this, or what is this equal to? And you don't need to panic about the integral part at all. You need to panic about the limit part. What do I mean by this? Is that the way you compute this, you just say, okay, I'm just going to write this as integral of 0 to a f of x dx, and then you just take limits when a goes to infinity. So you basically compute the integral separately, and then just take the limit of it. Now, the integral part, relatively no problem. The limit part, I'm not sure about that. So let's take an example of this, shall we? Let's do something that I know looks kind of nice. Okay. I don't know. Obviously, if there's, you can take a limit to minus infinity, take limit to 0 or 2, depending on the case. But I hope you got the point. Whenever there's a value that doesn't fit there, you just create like another variable and take a limit of it. This is the standard approach to dealing with it. Okay. It doesn't change anything in terms of computation. Here you just solve everything in terms of a, and then you take the limit of it. So let's just take an example of this. I'll just create one now. Hopefully, it's not terrible. So let's just do integral from 0 to infinity of one x squared plus 1x squared. Okay, I'm lazy. Let's do it like this. Well, I'm just taking this thing. It's their power function, so technically they shouldn't be bad. So now, as I said, we're just gonna write limit when a goes to infinity, integral from 0 to a, 1x squared plus 1x fourth dx. And now you can just proceed to solve the integral as the limit wasn't even there. Okay? So I'm actually gonna take it out. I don't really care about this. I'm solving it from 0 to a 1x squared plus 1x4 dx. And then we proceed how we learn. This is a separable one because I didn't want to waste that much time in doing like a complicated one. 0a 1x4 dx. And now hopefully I remember how to do these. This is equal to minus x. Minus x, is that correct? I hope. Minus x, yeah. Minus x from 0 to a plus. Oh, it's good. Well, we learned something. Maybe I shouldn't give double limits from the start. Okay, well, I'm gonna think about it. This is what happens when you create problems randomly. Give me 1 second. All right, let's just do, just to avoid this, because I don't want to show you a double limit thing. We'll do the other example after this. I think we have time. Yeah. Okay. We'll do the example afterward. Let's just put 1 plus x everything squared, 1 plus x everything to the 4th. Okay, let's just do that. Just to avoid problems that you're gonna see. So why did I change it? Okay, why did I change it? Because I couldn't plug in 0 here. Okay, if I had 1 over x and I needed to replace, I needed to have 1 over 0, which is not defined. Okay. In a non-limit setting. In limits, when you have 1 over 0, that goes to infinity. In real numbers, 1 over 0 does not exist. Okay. I've had surprise when I was quoted on this, on limits. So again, I'll actually write it out. So 1 over 0 does not exist in real numbers. Limit of 1 over 0 is infinity. Okay, let's agree on this. When you have limit of this, limit of x goes to 0 of x, 1 over x is infinity, since you're on limit. So you're allowed to put it in limits. You are not allowed to compute 1 divided by 0. But in limits, you're just saying it's something really, really big. Think of it as 1 over something very, very small. Or think of it as you have a cake. This one is your cake, and then you have x, which is like the pieces you're dividing the cake into it. If the pieces are really, 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 really small, how many pieces are going to have? Like you have a cake, right? Let's say this is your cake. This is your cake. If the pieces are big, if the pieces are like this, then I would have probably 5. Okay. How many would I have if the pieces are really small, like finer and finer? I would have an infinite amount of pieces of cake. Okay. This small piece of cake is x. It goes to 0, only like this small. Okay, that's it. Yeah. But I'm assuming he gave you the explanation of this, so I'm not going to dive into it that much. Anyway, so we have this integral plus this one, which is minus 1/3 1 over 1x plus the power 3. I'm assuming looks about right. From 0 to a. Okay, good. Now I just plug in my numbers and I get it. The first one is minus 1, 1 plus a, minus 1, 1 plus 0. There's the first one. The second one is minus 1, 3, 1 plus a, every the third, minus 1, 3, 1 plus 0. This is minus here. Gets complicated. So let's just put a plus 3, 1 plus 0. Okay. This is what I get. Just bring it all up together, and I get 1 minus 1 plus a minus 1 3 1 plus a to the third plus, what is this? Plus 3 plus 1 over 3. Okay, so this is my answer. Yeah.
Plus parenthesis. You have a parenthesis and then you have
Okay.
a minus.
Yeah. Yeah, well, that was a mistake on my part because there's a plus here. So this plus is here. Great call. Yeah, so just because I think I stepped on a bunch of you guys, I'll rewrite it nicely here. So I had this 1 plus x with a minus in front to integrate between 0a plus sign here, which I think I did it correctly, but I wrote it wrong. 0a. Okay. Now, what is this equal to? This part over here is equal to minus 1 plus a minus 1 plus 0 plus this part over here is minus 1/3 1 plus a to the third, and then I would have minus another minus 1/3 I can't write it here. 1 plus 0. Okay. I think we got the point. Anyway, so what do we get now? We get minus 1 plus a plus 1 over 1. Now, minus plus with minus gives me minus 1/3 1a plus a to the third. And then I have plus minus, so plus 1/3. Okay, this is my answer. So the integral, this is actually uglier than I expected. But this thing is just equal to 1 plus 1 over 3 minus 1 plus a minus 1 over 3 1. This one, I just copied this one. Okay, so I can compute the integral. Now, as I said, you just got to take a limit of it. We had to compute limit of this integral 0a 1 plus x squared. And I said, when a goes to infinity. And what I told you to do is just compute this normal, replace, and then take a limit. That is exactly what we're going to do. This is equal to limit when a goes to infinity of, just plug it in. 1 plus 3, 1 plus a, 1 3 1 plus a to the third. Okay, now it's got to be more or less a stupid question, but what is 1 plus 1 over 3 go towards when a goes to infinity? It just stays the same. They're constants. They're constants. When a goes to infinity, they don't matter. I mean, they're not effective. So I can just write this as 1 plus 1/3 plus the limit of a when it goes to infinity of minus 1 plus a minus 1/3 1 plus a. Okay, now let's evaluate this. A goes to infinity, this goes to infinity, 1 over infinity goes to 0. This is infinity, this is 0, so this whole thing is 0. Okay, awesome. So we just got this. Now, I'll do one really small example to show you another limit. Yes. Yeah, all good. Okay. The one example I wanted to do was integral of no, that's that. 1 over x from 0 to dx. And it's really simple because I want to show you something interesting. Like the problem is what's this integral? Well, just log of x, right? So this is just log of x evaluated between 0 and 2. The problem is log of 0 does not exist. Okay? That is the problem. The log of 0 does not exist. I've told many of you that it goes to minus infinity. Yes, but log of 0 itself does not exist. You can't, when you write log of 0, it doesn't make sense. So the way to deal with such problems is to write it as a limit. Okay? I will not, I won't. And I think most of the grades would be understanding. In this case, if you just wrote log of 0, kind of understand. But the formal way, for those of you that are interested, is to just say, okay, x can't be 0. So I'm going to say, I'm going to compute limit when, again, a goes to 0 of a to 1x dx. Does it make sense what I'm saying? Like the problem, if I just did it without limit here, is that I would have to plug in log of 0. Or how in my case, in the previous example, I had to plug in 1 over 0. Okay, that was a problem. So the limit just avoids this type of problem. Because you just get limit when a goes to 0 of log of x between a and 2. And then you get limit a goes to 0 of log of 2 minus log of a. And now you can make the argument, okay, a goes to 0, log of 0 goes to minus infinity. So, this goes to 0, the log thing goes to minus infinity, it has a minus in front, so it goes to plus infinity. Okay, does everyone kind of follow with that logic? Okay. Yes. Oh, are we on a break now? Sure, we can take a break right now. Let's take like a 10-minute break, and then we're gonna do some stuff again. So we've done this limit thing. I don't think it's gonna come up because obviously it's a really specific case, but in case it does, then you should know what they mean by it. When you see 0 to infinity or whatever, you should just understand that you gotta write as a limit and compute like it's not there kind of thing. Good, so that's it, unless there are any questions on this. Again, the by parts is really general. I've seen cases where some students applied it better than I would have, for example. So yeah, there's no particular rule for when to apply it or how to apply it. I just gave you those 2 examples because they are pretty, I would say, well known, or a lot of people know them. And there's a trap that if you apply it in a bad way, you're probably never going to finish. So now we're going to move on to substitution, which I was initially planning on doing next week, but I've been reorganized. So substitution, what does it mean? It just means you're replacing something with something else, right? Substituting. We all know that. Cool. Well, it seems that you can do that in integrals, okay? And here, I think substitution is like the true mark of skill, if you want to take it like that, because technically any problem can be solved by substitution if you're really, really good at it. I am not really, really good at it, but maybe you guys are. So, the idea is that if I have, let's do for an indefinite case, because the definite one has like one small thing to deal with. So let's say we have an integral of g of some f of x. For example, what do I mean by this? We just have e to some x squared plus 2 times x. Okay? It's just ugly. Let's just say I'm interested in getting rid of this x squared on the denominator, on the exponent, right? I have 2 powers. That's like ugly to deal with. Never something good. The idea is that you can just write this, change it. If you just have this f of x as an equal to u, then you can write this as being integral of g of u du. Be careful. I've changed the variable after which I'm integrating. I'm not integrating over dx. I'm integrating over du. Okay? With the small thing that du is equal to dx times f prime of x. I know this looks like somewhat complicated, but I'll take an example and hopefully gonna look a lot nicer. So let's look and okay, let's take this one. Let's take this one. Integral of, let's say, x integral of x plus 1 dx. Okay? In case, for those of you that know or come to ours, whatever, I hate square roots. I hate complicated formulas under the square root, and substitution usually solves that, because what I can say is like, I don't want to deal with this. Plus, I don't know how to solve it. Maybe there's some by parts here, although it's a really ugly one. I don't know, I'm confused. So the way to simplify it really, really nicely is, okay, let's just say this x plus 1 is just equal to some u. Okay? All right, u is equal to x plus 1. Then, if I take a derivative, I'm going to get du here is equal to derivative of the formula above, so x plus 1 dx, okay, which is a small 1 times dx. Okay, everyone follow up to this one. So basically, I just said, okay, I hate having stuff under the square root, so I'm just gonna replace it with an x plus 1. I'm just gonna replace that with a u. Then the way I compute the new du, according to the formula above, is I just multiply dx and take the derivative of the formula that I replaced it in. In this case, x plus 1, derivative of x plus 1 with respect to x is just 1. Okay, so now I can change this as integral. So we're gonna do it step by step. X square root of u. Instead of x, I put du. Instead of dx, I put du. Now, is this writing correct? Am I done with this with the change? No. The problem is right now, and this is the biggest mistake I've seen in substitution, is after you substitute, you can't have both variables in. You can't have x and du. If there's du here, I need to have only u everywhere. Okay? So this, if I leave it like this, is wrong. For step by step, fine. But if u is equal to x plus 1, then it means x is equal to u minus 1. Right? So I can just replace it. I can just say, okay, so this is actually integral of u minus 1 times square root of u, du. Okay? So again, my idea was, this is the simplest, one of the simplest examples I could think of. Obviously, we're going to do something more complicated to see the actual power of it. But you know, I had square root of x plus 1 here, dx. This is really ugly to work with because I don't know how you take the derivative of that, or I don't see it, etc. So I thought, okay, let's just replace this x plus 1 with a u. Okay? Now I computed the du. This is the next step you have to do. You need to compute du. Compute the du, which is I just take the derivative of the thing of the function here, x plus 1 with respect to x, and slap a dx on it. So this is just 1 times dx. Okay, so du is just equal to dx. Cool. I just put equal here and I replace with, and I have the integral, x I didn't touch, square root of u, that was the whole idea of my change, times du. Now what I said was, there's a problem with this, that now I have x and u in the same integral, which is wrong. That's bad. You can't, it doesn't make sense. So I need to get rid of that x. I need to write that x in terms of u. So I thought, hey, okay, if u is equal to x plus 1, then x is just equal to u minus 1. So what I do is I just replace this x with u minus 1. And now I have to solve this integral. And you might say, okay, but this doesn't look much better. Well, if I just open the parentheses, I get integral of u times square root of u minus square root of u du, which is equal to integral, you know, I can just split it, and I have u times on the power of 3/2 du minus integral u a half du. And this is much, much better because you know you can use the formula for powers or whatever. So this is just following on the next page. Is just equal to what is this equal to? Okay. It's equal to u 5/2 times 2/5 minus u 3/2 times 2/3. This is just a formula that you use from the book, or you know, whatever. It's a power integral, so I'm not worried about that. Plus a constant. So I was able to solve it pretty neat. Now you can't leave it like this. In the indefinite integral, you cannot leave it like this. What do I mean by this? Your integral was x square root of x plus 1 dx, and you computed it to be equal to this, u 5/2, 2/5 minus u 3/2, 3/3, lots of constant. What did I tell you? X equals to u. Apples equals bananas. Not okay. Okay, I gotta replace the u back. So now I'm just replacing the u is equal to x plus 1. I'm just replacing it back. I'm just replacing it. X plus 1, the 5/2 times 2/5 minus x plus 1, 3/2, 2/3 plus a constant. Okay? In the indefinite integrals, always replace your u back in. I ask you, you know, this problem, this integral, I ask you, what do I get if I just integrate the temperature of the earth, and you tell me, oh, that's equal 5 apples. That's really what you're saying right here. It sounds stupid, but it's really what you're doing. You need to give me the answer in terms of x. I give you the integral with x, so dx, I need to see x on the right side. Okay? Now, let's give another example, one much more powerful example. You would think that if you complicate an integral, it gets complicated, you know, the answer is more complicated. That is true for the general case, not for the substitution. It just works magically sometimes. Here, let's take this example. Over here, okay? What I do, I just put an x squared here. Technically, it should get much, much worse, right? Well, let's see. I'll just use the substitution method again. My intuition is what's underneath the square root is bad. So I say x squared plus 1 is equal to u. Okay? Good. Now, what I said, what did I say was the next step? Just take a derivative of this thing with respect to x. So I get 2x times dx is equal to du. Everyone follow on that? This derivative, you know, just derivative. Derivative. Okay, now we're in a bit of trouble right now because let's see, if I replace it blindly, I get square root of u times x dx. This is horrible because I have dx and I have u here, doesn't work. We already talked about that. Can I do something? I need to get rid of x and I need to have a du pop there. Well, look at it. 2x dx is equal to du, and I have an x dx. Any ideas here? Yep.
Minus u times 2 du, like square root of u times 2 du.
Times du over 2, maybe. Yes.
Oh yeah.
Yeah. So the idea is that, okay, 2x is equal to 2x dx is equal to du, and I have an x dx. So I can do some stuff here. X dx is just equal to du over 2. Right? So what if I just plug this in? Okay? If I plug it in, I'm going to get okay. Now, the whole idea is that I can write this as being equal to the integral, of course, being equal to integral square root of u times du over 2. Everyone see it? Everyone got it? Like this is why I call it like magic, because sometimes if you complicate a problem, it just gets better. It just gets simpler. So this is just equal to a half integral square root of u du, like 10 times simpler than before. So this is just equal to a half times here it comes again. What's this integral? 2/3 times u to the 3 over 2. If you memorize the formula, you would be much better off because I need to pause like 10 seconds to remember every time. Is this the one? Looks about right. Okay, plus a constant. Like, see what I mean? That sometimes it just works out perfectly if you apply the substitution how you're supposed to. All right, am I done? No, I need to give the final answer. X square root of x squared plus 1 dx is equal to 1 over 3. If this goes away, u 3 over 2 over c. Again, remember, apple, bananas, not okay. So I just plug it in and I get 1 over 3. X, my substitution was this, x squared plus 1. So I have x squared plus 1 to this power that I don't care about, plus a constant. Everything worked out perfectly. Now, if you ask me, how would I solve this without the substitution? I'm saying I don't know. I'm saying I wouldn't try to do it. You probably can do it with the by parts, but it's not going to be an easy one or a nice one, I think. But luckily, I don't care. So yeah, that's the substitution. It's not much to it. Yeah, let's take another example. Let's do a fraction, maybe. It's fun. When you go for part? Let's take this fraction. Yeah, I like it. Okay, let's take it. Like, you gotta remember that the whole trick, the whole exercise that you have with this is getting the practice to know where and how you can split your, or you can do the substitution. And I wish I could, but there's, you can create a problem that looks different than any other that solves for substitution or through the by parts. So you just got to figure that by yourself, when and how to apply it. I'm just showing you how it works and giving you some cases, but unfortunately I can't do more than that. Now, in this case, this one looks pretty bad. I don't know what to say. I guess I could do some log stuff and play with the fractions, but that would require like a lot of ingenuity to make sense to solve it. Like I could solve this by hand, but it's gonna take me longer, uglier, and definitely not intuitive. So that's why I'm thinking, let's just try it by parts, see if it works. What substitution am I thinking of? Well, it's only one candidate, right? It's just this one. I'm just gonna try it. I don't know if it works, but it's worth a try. That's why I said, I think, in workshops, I've always said that it's good to have a computational practice. Basic idea: the faster you are at computation, more ideas you can try out. Eventually, you'll get the solution. Okay. That simple ideology of basically being stupid and trying all the things that come to my mind carried me to like international. So it's you might think it's like this is so brain that it doesn't tell mathematically. It's literally what everyone at the International Math Olympiad are doing. They're just trying things until they get a solution. Okay, they're just trying. All the ideas are good as long as you can check them. So I'm just saying u is equal to 1 plus t squared. Now take the derivative. Du is equal to what's the derivative? 2t dt. Okay, let's see what we get. Yeah. So for now, I get integral 1 over u t to the third dt. Okay. You got to realize you're in a bad situation. You have t and u in the same thing. Not gonna fly. So let's see what we can do. I see a t dt here, and I see a t dt here. Okay, so now I'm just like, can I just do something like this? T squared times t dt. Okay, I just split this. I just split this t to the third and like 2 t's and 1 t. Why did I do that? Well, because I noticed there's a t dt here, so I created my own t dt here. And again, same logic as before. I can write this as integral 1 over u t squared and t dt. This is just du over 2. Everyone follow on that? I'm just replacing it step by step. Obviously, in an exam or something, if you see it, you just replace it immediately. Obviously, you don't need to write all these steps. Okay, now, am I in a good spot? No, I still have t and u. I still need to do something. What is this t squared? Well, I just look here and I get, oh, u minus 1 is actually equal to t squared. Okay, so I just put it in. So I get integral u minus 1 u du and over half, let's put it here. Okay. Now again, as I mentioned in the by parts, it's important sometimes to just stop after you do the substitution for a second and assess, am I getting simpler? Am I getting more complicated? If you're getting more complicated, then obviously the substitution didn't work, okay? You need to get simpler stuff. So, and did I get simpler? Well, this is what I need to compute, and we started here. So I'm gonna say, yeah, we definitely did something. It definitely looks much better. Okay, so now let's just solve this one. Again, I'll go again through the changes I made, because this was, I guess, more complicated in the sense that I need to do more of them. So I started with this integral, okay? Everyone stop writing, because I'm just gonna explain it. So this is 1 plus t squared. I just get the idea that's the only thing I can replace technically. There's nothing else that's gonna make a lot of sense. Maybe t squared, but again, debatable. So yeah, you can solve it. You can actually do it if you just replace t squared. As I said, there are multiple ways which you can do it. You can try it as a practice. But my idea was just 1 plus t squared. This is my substitution. Once you write this, you gotta compute du and dt, their relationship basically. So what I do is, okay, du is equal to take the derivative of this thing, 2t dt. Okay, this is my du, this is my dt, my substitution is here. This is the standard structure of like applying substitution. And I would just apply it. So instead of 1 plus t squared, I write u and I get 1 over u. Okay, that's good. I don't change anything else for now. I have t to the third dt. Now, this is bad because I have u and t in the same integral, not gonna solve it. So what do? I put equal and I write 1 over u. And here is like, I spend a second and I'm like, yeah, I have this du is equal to t dt. Can I just create that? Can I just, I don't know, I'm trying to get rid of stuff. And I say, okay, split this t to the power of 3 into t to the power of 2 and just t. Okay, I just split it. Why? Because I saw this t dt here and I wanted to make my own t dt here. That's the idea. So now I rewrite my integral and I say, okay, 1 over u didn't change, t squared didn't change on the other, but what is t dt? It's just du over 2. Okay? So now I'm getting there. I have u here, I have u here, I have t here. I need to get rid of this t squared. Now, because I started with u is equal to 1 plus t squared, it means just that this t squared is just u minus 1. This is just u minus 1. So now I'm good. I have only u in my whole integral. And now I can compute it. And this integral is so nice to compute. Why? Because if you just write it out, just put a hat in front of it. U minus 1, u du is equal to, split it, u over u minus 1 over u du. Split it even more, 1 over integral of 1 du minus a half integral of 1 over u du. Okay. Now I can just write this is just 1/2 u minus 1/2 log of u plus lambda constant. Done. Okay. And okay, partially done. I need to plug in the values. Okay, don't forget about this. So I get, it helps to rewrite the answer. I never had that habit, unfortunately. So I get u plus minus a half log of u plus a constant. Again, I remember now u was equal to x squared plus 1, xt squared plus 1. Yeah. So this is equal to 1/2 t squared plus 1 minus a half log of t squared plus 1 plus lambda constant, and I'm done. Okay. Any questions on this? You have a nice Go on. So any questions? Nothing? Okay, so everyone is pretty lost. We're great. Cool, now let's do the substitution to the definite integrals. I said there's a small twist to it. Substitution to definite integral. So, the only change is that we're gonna have, when we do the dx dt, we're going to change the limits of integration as well. And for this, we'll take like this really easy example before we go on to an actual idea. So let's take, remember when I asked you to show something like integral from -10 to 10 of x dx is equal to 10 or is equal to 0, something like that. I gave you some random power. I could have given you any power. But this was the basic problem. I think I gave you some x to the third or something like that. Okay? Let's try and solve this by substitution. Here, using my trick. So I'm going to split this -10 to 0, x to the third dx plus integral 0, 10, x to the third dx is equal to 0. Okay? Now, let's apply a substitution to this. I'm going to apply u is equal to -x. Okay? So now du is equal to -dx. Everyone follows what I'm doing? I'm just applying a substitution there. And now comes the extra part. So this we were doing in the indefinite case. Yes. Because when I apply -x, I'm just gonna show that this integral is gonna be minus this one. That's why I chose -x. Because you see that the way you see it is that they're the same integral, right? But one of them is from -10 to 0, the other one is from 0 to 10. So it makes sense to consider the opposite. Okay? So this is the indefinite. These are the conditions for the indefinite. Now, for the definite, I have to change my limits of integration. Okay? So I'm adding from -10 to 0. Now, if I say I want to compute the variable where u is -x, it means I'm going to add from sorry, you just put, if x is -10, then u is going to be -10, so that's +10. And if x is 0, then u is going to be -0, which is just 0. I'm just adapting my limits of integration to my new function. Okay? These are the definite conditions. So, what I get is integral from 10 to 0, x to the third. What is x to the third? Well, if I just raise this to the power of 3, I get u to the third is equal to -x to the third. So this is just minus u to the third. Instead of, I know that du is equal to dx, so I replace dx minus du plus integral 0 to 10 x to the third dx is equal to 0. Everyone follows. So the only thing that's different in the definite case is the fact that I need to change my limits of integration. That is the only thing that changes. All right, now let's see why I chose this way of writing. So plus, minus with a minus just becomes plus. And remember, I'm gonna rewrite the formula again in case you forgot. I'll write it here. Integral a to b of f of x dx is equal to minus integral from b to a of f of x dx. Okay? So I do that here, and I get minus integral from 0 to 10 u to the third du plus integral 0 to 10 x to the third dx is equal to 0. And now I hope you see why I'm saying that it's equal to 0. This thing is the same as this thing. It doesn't matter that if it's it's u to the third du, this is x dx. It doesn't matter, it's still the same variable. The limits of integration are the same. This has a minus, this is just that thing. So when I add them, it's going to be 0. Now, in this particular case where you had integral x to the third, you could have just computed it, right? You didn't need to do all this smoke and mirrors, whatever. But I can solve it this way with the substitution for almost any function you give here for me. Any, I think it's called odd function. Any odd function you plug in there, which is like a huge amount. So there's like a general way. You just solving this integral and plugging in minus 10 and 10 and showing me that it's 0. It's a specific way. Sometimes you might not be able to solve this integral, and you might need to do it this way. Okay. Now let's take a more educated example. Let's say, let's take this one. I'm going to take integral from 1x log of x dx, let's say from e squared. Now, disclaimer, yes, I know you can solve this with the by parts thing, okay? Because this is just integral x minus 1 over log of x. You can solve this with the by parts probably. But I'm here to showcase the substitution, okay? So let's do the substitution. What's the ugliest thing here in this whole function, in this whole integral? What's the ugliest thing? The thing that if you could get rid of, if you would get rid of, everything would be nice. You would be able to solve it. That log of x. Remember, I told you, integral of log of x is nasty to deal with. You don't want to deal with that. So I'm just saying, okay, u is equal to log of x. See what happens now. Take a derivative. Du, what's the derivative of log of x? 1 over x dx. Am I done? No, it's a definite integral. So I need to change the heads of substitution, or the heads of integration. Again, if x is equal to e, this one, then it means, if x is equal to e, then it means u has to be equal to log of e, which is 1. If x is equal to e squared, then it means u is equal to log of e squared, which is just 2. Everyone follows on that? I'm just changing, according to my new formula here, I'm just changing these values over here. That's all I'm doing. Okay, now I'm ready to actually do some replacement. So this is equal to integral. Instead of e, I'm gonna write 1. Instead of e squared, I'm gonna write 2. Okay, what do I have left? I have 1 over x. Let's do it the other way. I have 1 over log of x, so that's 1 over u. Okay, times 1x dx. So let's do a recap. I changed my limits of integration, that's good. I changed my log of x, that's fine. I still have x and dx, that's really not fine. That's bad. So I need to get rid of this. How do I get rid of it? Well, you look here. A apparently that ugly 1 over x dx is just du. So this is just equal to integral 1 over 2, or 1 from 1 to 2, 1 u du. Now, if you have changed your limits of integration, your heads of integration, so basically, since I changed from e to e squared, I don't need to change back because I'm just gonna get a number. This is just gonna be equal to log of u from 1 to 2. This is just gonna be equal to log of 2 minus log of 1, that's just log of 2. Okay? So what did I say? Again, careful. On the definite integral, if you have changed your heads of integration, you can just compute according to the new u. Okay? Because you're still getting a number. In the indefinite case, if you were giving me the answer without replacing, you would just give me something like t is equal to u. Here I have no u, no x, I just have a number. It doesn't matter if I compute it by replugging in x here and doing it. Let's actually do that. Let's actually convince you that it's the same. So let's actually convince you that it's the same. So my integral, so you get this if you just straightforward replace after you compute. Now, let's say I have this e squared 1 x log of x dx is equal to this. Now I just got to replace everything here. So I just replace log of my notation was u is equal to log of x. So I get log of x from e to e squared. Okay, this is just log of u. And now if I plug these in, I'm going to get ln, but whatever, minus ln of e. So it just gets log of 2 minus log of 1. This is 0, so I just get log of 2. You get the same result. Either if you get back, plug in the x, and then evaluate it at the original limits of heads of integration, or after you have done the computation, you just continue and finish with the u thing. You're gonna get the same result in the definite case. But yeah, I think that's kind of it there.